Hello everyone, today I want to show you how to solve this differential equation up here. So in my previous video I explained what a homogeneous differential equation is, and today I want to give you an example. So remember that anytime you have, in my opinion, anytime you see a linear differential, anytime you see a linear expression, you should either think of using separation of variables, because sometimes you can do that with linear functions. You could either think of treating your differential equation as a Bernoulli equation, or you could try using the method of the integrating factor, or you could try treating your problem as a homogeneous differential equation. In this case, we have two linear expressions. We have x, y, nothing is raised to any strange power. So that means that, well, this is going to be a homogeneous differential equation. And you can tell that just by observing it and thinking what's going to happen if you multiply x and y by a factor. So remember that to treat this as a homogeneous differential equation, we first need to check if the right-hand side of the equation satisfies the following property. So if we say that the right-hand side of the equation is f of xy is going to be some function, we need to check if f of t times x and f of t times y is equal to f of x, okay? Now, what this equation is telling you is that if you multiply the arguments of f by some factor t, you should get back the original function. Now let's check if that happens with this expression. Let's say I'm going to multiply, let's use t. So if we multiply x and y by t, we're going to get 6t times x minus t times y divided by t times x plus t times y, okay? Now notice that you're going to be able to factor out a factor of t, and you're going to get back, well, the original function. And that is the reason why you can treat this as a homogeneous differential equation. Notice that when you multiply x and y by t, you're going to be able to factor them out in the end, and they will cancel out, and you get back the original function, okay? That tells us that we can treat this as a homogeneous differential equation. And when you have a case like this, that means that your right-hand side of the equation is a function of the ratio of y to x, and that allows us to make the following substitution. Let v, I like using the letter v, let v be equal to y over x, okay? Now, we want to rewrite everything in this equation in terms of v and x, okay? So let's begin with dy dx. We know that, well, we can find dy dx, first of all, by saying that y is equal to v times x, based on the substitution that we did. And then we can say that dy dx is going to be equal to, so we can use the product rule on this. We're going to have dv dx times x plus, and then we have v times the derivative of x with respect to x, that's going to be 1. So this is our substitution for dy dx in terms of v and x. Now what about the right-hand side of the equation? Well, I'm going to continue here, because this is just dy dx, so I can set this equal to the right-hand side of the equation. The right-hand side of the equation, using our v notation, is going to be 6x. Remember, x is a letter we want to keep. Minus y, we can write y like this, so minus v times x, divided by, and then we have x plus y, that is going to be x plus v times x, okay? And now, in all of these problems, if f of x, y is a homogeneous function, you will be able to factor out an x, okay? And that's going to give you a really nice separable differential equation. That will always give you dv dx times x plus v is going to be equal to, so if we factor out an x from here, we're going to get 6 minus v and 1 plus v in the denominator. Okay, the only thing I did here was I just factored out an x. Okay, so you get an x in front and an x in front, both in the numerator and the denominator, and once again they will cancel out, and you get this nice expression. And this is actually very easy to solve. We can just use separation of variables. We solve for v, and once we have v, we undo our substitution to get y. Okay, so let's do that. So I think I can. No, I'm actually gonna continue up here. I don't like crouching. So I'm gonna continue up here. So I'm gonna move v to the right hand side of the equation, and that means that we are gonna get dv dx times x is gonna be equal to 6 minus v divided by 1 plus v minus v. Okay, this is what we have. And I'm going to simplify the right hand side of the equation so that we can get dv dx times x is going to be equal to, so let's just simplify this in a better way. This is going to be 6 minus v, and then minus v times 1 minus v. So I'm going to write out the entire thing and not try to force you to understand what I'm saying just based on words. I'm going to write the expression. So you just multiply the numerator and the denominator of this term by 1 plus v, okay? I hope you're familiar with that. And then let's see what we get. This is dv dx times x is equal to, so we are going to have 6 minus v minus v minus v squared divided by 1 plus v, okay? And now, I like to continue down here. dv dx is equal to, so overall what do we get? So we get minus 2v and minus v squared. Is there anything else we can simplify? Nope, but that's okay, because even though this looks a little hard to integrate, you're gonna see that we can do this integral that we're about to do with u substitution in a really clever way, in my opinion. So here's our separable differential equation. This is fully simplified. Well, technically not, because I mean you could factor this into 1 plus v again, but you would be undoing what we just did, so don't do that. So now, let's do separation of variables. So I'm going to multiply by the reciprocal of this on the left hand side of the equation, and we are going to have 1 plus v divided by 6 minus 2v minus v squared, and then this entire thing times dv, and this will be equal to dx divided by x, okay? And now we just want to integrate. So we want to integrate both sides of this equation, okay? And that's going to give us an expression for v. Now, this may look a little hard. Most people would go straight and do partial fractions. That could work, but I think there's something much better you can do. I'm gonna say let u be equal to this entire trinomial, which is really annoying to deal with. And then you're gonna get that du is going to be minus 2 minus 2v, right? You just differentiate this, and this entire thing times dv, okay? Now notice something pretty amazing. You can say that, I'm crouching now, that's fine. Minus 2 times, this will be equal to minus 2 times 1 plus v dv, okay? And notice that 1 plus v dv is what we have in the numerator of our integrand. So this is wonderful because we can just rewrite the numerator as du divided by negative 2, okay? So let's continue here. We're going to have that this integral becomes, so we have the numerator is just going to be minus a half, so minus a half comes out in front. Then we have du divided by u, because u is this ugly expression that we try to get rid of. Then the right hand side of the equation is going to be the integral of 1 over x, that is ln of the absolute value of x, and we are going to get a constant, okay? That constant is very important. You'll see why in a moment. And then we can just do this integral, so this becomes minus 1 half, and then that's going to be ln of the absolute value of u. We know what u is, so I'm gonna avoid writing the intermediate u. And I'm just going to say that this is the ln of 6 minus 2v minus v squared, and this is equal to the ln of x plus c, okay? Now, once we have this, our goal is to find y as a function of x, and v we know is a function of y and x, so we could just undo the substitution, okay? But before we do that, I'm gonna simplify things a little bit. First of all, I'm going to multiply both sides of the equation by -2, and we are going to have ln of 6 minus 2v minus v squared is equal to -2 ln of x plus c, okay? Now we're going to exponentiate both sides of the equation, and if we do that, we know we will get 6 minus 2v minus v squared is equal to, we're going to have a constant, so let me actually do this like this. I'm going to say we're going to have a constant, a, which is going to correspond to this, and then we are going to have, remember that when you exponentiate this is the same as doing e to the ln x, and then all of this to the -1/2, okay? So overall, this will just become a x to the -1/2, okay? Not -1/2, sorry. Did I say -1/2 before? I meant to say -2, okay? And now I am going to multiply, so this is the same as doing a divided by x squared. So I'm going to multiply by x squared on both sides of the equation, and we're going to have x squared times 6 minus 2v minus v squared is equal to some constant a, okay? And now it looks like we're not going to be able to solve this in terms of y explicitly. So I'm just going to undo the substitution, and I think we're going to have a form in which we have a function of x and y in terms of c, which is a totally valid solution. It may not be the most useful solution because typically we want to know y explicitly, but that's okay. So overall, we're just going to have x squared times 6 minus, so we had v equals y over x, so minus 2v, that is minus 2y over x, and then minus y over x squared, and then this equals a, okay? And this would be our final answer. If you differentiate this with implicit differentiation and then you solve for y on the left hand side, you should get back to the original differential equation, okay? So yep, this is how you can solve this problem. When you have differential equations like this, check if they're homogeneous, and then just do the substitution, and then all of this should be fairly easy. Sometimes you're gonna get an integral that can only be solved using partial fractions, in which case, well, you should feel comfortable using partial fractions. But yeah, I hope you learned something from this video. I hope you had fun, and I hope to see you in the following one. Bye.